Electrical safety. That's what we're going to be talking about for roughly the next hour or so, and we're going to try to cover all types of different aspects of electrical safety that you find in the trades industry. Why do we talk about electrical safety? Well, when you think about it, it's very, very difficult to do any tradesman job without having electricity involved. But just think about that. How would we deal with power vented water heaters if we couldn't work with electricity? How many of you HVACR technicians are out there that, in order to mechanically diagnose your projects or your appliances, you have to understand some electricity? Electricians spend their careers learning more and more about how to keep themselves safe, what particular situations present dangers, and what type of dangers they present. However, the rest of us in the trade industry only learn enough to get by oftentimes, which is where we get into trouble. We always feel safe. And if most of you are similar to myself, there's really nothing we can't handle. In our own minds, that is. In reality, there's a lot of things we work on that we probably just shouldn't. And we don't think twice about the repercussions for our lack of understanding of those subjects, but we really, really should. So that's why we're going to cover this particular subject. When it comes to electric current, regardless of how small the current is, or whether they're encountered in the workplace or even at home, they could be sufficient to cause serious harm, like burns, both internal and external, blindness, or any variety of injuries related to falls, even. Obviously, the worst case scenario is death by electrocution, which, by the way, is something important to point out. When it comes to a true electrician, a person that's electrically licensed and so on, so forth, the word electrocution and shock mean two different things. Now, in the other trades industry, we throw those around like they're no big deal. However, in the electrical industry, the difference between electrocution and shock is one you walk away and one you simply don't. Now, you may be working with coloring books for a little while, but you made it through if you've been shocked. Electrocution, well, electrocution's the end of the ball game for that individual. So workers in the HVACR industry, generally make our living working around electricity. We have our exposure time elevated anytime we're on installation, almost every time we're on any kind of maintenance or repair, and we work on high and low voltage systems. So constantly being exposed to those types of environments require us to have an extensive knowledge even beyond the mechanical industry. It's important to understand and recognize the electrical hazards and the methods of preventing electrical shocks and other related injuries. And of course, we want to be able to prevent electrocution. On average, one worker in North America is electrocuted every day, making electrocution one of the leading causes of death in the workplace, especially among young workers. Over half of all the electricians and electrical injuries are suffered by workers who are working on systems with voltages less than 600 volts. So our idea of electrocution only happens at high amounts of voltage is not true. Oftentimes it's at lower voltage, lower than 600 volts. When it comes to electrical safety, the one thing you got to keep in mind, and it's one thing that's basically followed throughout the National Electric Code. Make sure that you don't electrocute the individuals, and make sure that you don't burn the building down. Well, today we're going to talk a little bit about both of those subjects, but the first thing we're going to talk about is protecting yourself or others around you. Obviously, the body can become a path for the current. When it becomes part of that electrical path, it doesn't just go through the body, it goes through all the paths. So even though I become part of that electrical circuit, I'm by far not going to be the path of least resistance, which a lot of people make the mistake of thinking. In fact, the human body has resistance of anywhere from 100 ohms to 1 million ohms, depending on uh, the size of the individual, the humidity, water content, the makeup. All of those things can go into effect when you're calculating what the resistance of the human body is. If you're curious, just grab a meter, especially if you've got an analog meter. They're great for the sensitivity that's required for this project. Put it on resistance and just simply hold on to each of the leads, the positive and negative. See what it gets from fingertip to fingertip, one hand to the other hand. It's pretty interesting. Try it several times throughout the day, or maybe several different days throughout the week, and you'll see that your resistance will change based on varying conditions. Remember, the lower the resistance in the body, wet hands, feet, cuts, scrapes, etc., the higher the current flow through the body. When it comes to electric burns, they're caused by current breaking through the skin, and it's not always going to be visible. Now think about this for a second, if you would. We've all heard about electric shocks, and we've all seen pictures of what a sine wave looks like. And we know that once we get to three-phase voltage, it's virtually impossible to let go. Well, it's virtually impossible to let go because there's no peaks and valleys. There's three different sine waves all in one, and when one is starting to go down, the other one's starting to come up, and there's no time within that pulsating range that you're going to be able to let go. So, in looking at it that way, and you look at normal AC 120 volts, it's possible to take a shock and live through it. It may not be possible for everybody. Obviously, people die at that voltage every day. But when you look at it from that point of view and you go down lower in voltage, even to our 24 volt thermostat, the voltage isn't the key. It's the amperage that goes through it. And we'll look at a chart here in a little bit to see how that amperage affects the human body. But picture with me, if you will, a small amount of voltage, a low voltage wire in your hand. If you've got a low voltage wire in your hand, first of all, even us biggest guys are going to cry like a little baby, when we first get shocked. We think it's the biggest thing in the world, and then sometimes we feel foolish. Maybe you don't cry, maybe you jump. Maybe the cry was a little bit harsh. But if you're just sitting there in a chair like I am, and you're holding a fist, eventually inside of your palm you're going to start to sweat. You can't help it. It's just the way it happens. The body conducts heat, and to get rid of that heat, we're going to try to sweat it off. So imagine a wire being in there, and that wire pulsating to the point to where you can't let go of it. It's just enough to where you can't let go. It's painful, but it hasn't killed you. Then you start to sweat. The sweat puts that moisture all over inside of your palm, and while it's all over inside of your palm, that amperage is now being amplified to all different sections of your skin in your palm. Eventually, that amplification is going to burn through the skin. Once it burns through the skin, what's in the middle of your hand? All kinds of little capillaries and arteries and veins and things like that. They're going to be a great conduit straight to your heart. So it's not just the voltage that's going to get you. It's not just the amperage that's going to get you. It's the method in which you get shocked. All of these things line up in a certain fashion, and it can happen even at low amounts of voltage. Some of the damages that can be caused could be blood clots. And that's fairly common. It cooks your blood. I mean, you think about it. Electricity, when you look down inside of a electric strip, a air handler with electric strips, you got just a bare wire. It's all coiled up. And because it's all coiled up, there's work being done. It glows red hot. A lot of heat's put off. Well, when you think about it, the same thing's happening right there in your hand. It's going to cook your blood. It could cook your digits. One of the worst feelings in the world's got to be being able to see your hand or your fingers or your leg or whatever scenario that you can imagine, and knowing it's there, but knowing it's not going to be there for very long because you've fried your digits, you've fried your flesh. It can virtually vaporize muscle tissue. It can give internal organ damage. You can have permanent nerve or even brain damage. Blindness is another one that's not uncommon at all. And that blindness could be temporary, but it could also be permanent. So there's all kinds of things that go into electrical safety that you may not have thought about or even took serious. And then, of course, you add to that falls. Now think about that. You've been shocked by low voltage before. Maybe even stuck a 9 volt battery on your tongue and it made you jump, right? It's a silly little trick we play when we're kids, or maybe a frat trick or something like that. But think about that. Think about being up on a ladder and you take a little bit of a jolt, low voltage or otherwise, and just for a second, you forget you're on a ladder, correct? But guess what? The ground's going to be right there to remind you you were just on the ladder, and it's going to catch your fall, but it isn't going to feel good. Fall related injuries are huge, especially when dealing with electricity. Electrocution is often associated with high voltage, and we briefly talked about this already. And when we're talking about electrocution, it's important to note we're talking about somebody that didn't make it. Um, High voltage is not always what we're looking at here. The amount of current is really what the factor is. So when you look at it, uh, electrocution and injuries from electric shock can really occur at any voltage, provided the appropriate current is there and available. Most of the time, you hear about the high voltage shocks, and they do result in injury or death. But that's because, generally speaking, the higher the voltage, the higher the amperage as well. Not always the case, but oftentimes the case. So at first glance, lower voltages might not be very dangerous. But if the conditions are right, it could be fatal for you. So make sure you're always taking precautions to protect yourself on the job site. There's nothing worse than trying to hurry to get something done so that you can be to an appointment on time, or your kid's baseball game, or a wife's open house or something like that, and an accident occurs because you're trying to rush. There's nothing worth that. Here's some of the indicators of electric shock, or not indicators of electrical shock, but things that could lead to electric shock. Sources. Exposed wiring. Well, hopefully that's not one of the things that you're dealing with. If you're dealing with exposed wiring, you got all kinds of other issues. You walk up on a job site and you've got exposed wires. The first thing that I would be thinking is, oh my goodness, if it's right here where I can see it, how much more exposed wiring is in areas that I can't see? Frayed cords. Frayed cords on a job site are critically evil. And if you have an OSHA official that comes out there or a safety monitor that comes out there, oftentimes if you've got frayed cords, they're going to cut the end off them. They may even cut them in half. So that you're forced to go out there and get another cord. They're dangerous, and there's no amount of danger that's going to be worth putting up with to get the job done. Uncovered panels, again, if you've got uncovered panels, hopefully we've got some kind of markings there that indicate that, and there's an electrician there that's working on that. But uncovered panels are always a danger. Not just a danger because you could stick your hand in there. That's not what we're oftentimes worried about. We're worried about what's in the air, what's in the space between you and that panel. Even if you're just walking by, if the conditions are right, you could literally create an arc from that panel to your body if you're not protected. Missing wire markings are all too common. We've all run into those on the job site where you go out there and you thought one of those three wires was the neutral or the ground wire. You hook it up, Turns out it wasn't. You create a huge flash, or um, you've tripped some expensive, uh, effective ground fault path type of device. You've blown some fuses, and that all comes back to missing wire markings, which could have been prevented at the onset of the installation of this job. So make sure, if you're out there, we can't control what other people do, but you're the one that's listening to this presentation. So you're the one that's actually taking the initiative to get involved and do things the right way and be safe on the job site. So make sure when you're on the job site, you're not doing that same thing. Always label your wires so people know what goes where, especially if color coding is an issue. Improperly installed connectors is another huge thing that we see out on the job site from time to time. Maybe you've got the wrong temperature designation on the terminals that you're using it for the job. Maybe you've got just the wrong terminations on the end, wrong connectors in general, or maybe they're double lugged. All of those things have to be taken care of because they can relate to tragedy, whether the building could burn down because of an additional amount of heat that's created because of those improperly installed connectors, or somebody could get dangerously hurt. Loose terminals is another one. Always check your terminals when you're having an issue with heat building up in a line, or potentially prematurely tripping breakers. Loose terminals are kind of a fickle subject. When you think about it, if you go out there and you've got aluminum or copper wire going up into a terminal, as soon as you apply power to that, there's heat inside of that wire. Both of those metals are going to expand and contract with varying amounts of heat. It is possible that as it expands, it either crushes down the wire a little bit because it's snugged up already and there's no room for expansion, so it crushes it a little bit, or it starts to work out that lug on the terminal. Well, then once it cools down for whatever reason, now it's going to be a loose terminal. And stripped insulation is also one thing that happens that's easily prevented. Generally speaking, when we've got insulation on a wire that's stripped back too far, so that it's hanging out of the wire nut or the terminals, obviously can create a hazard for any individual, and then also for the building as well. We've got bare exposed wires, which brings us full circle around to what we were just talking about. All of these things are easily preventable, and that's why I bring them up. They're not something that will spend you all, or will take you all day to go out to a job site and verify they're not there. They're things that you could go out quickly, fix if they're an issue, but mainly as you're installing something for the first time or brand new after a retro, you can make sure that all of these things are in check when you leave, so that it's right from that point on. And that's really what we're trying to do in this particular presentation as well. Electric shock. The body can act as a conductor, and we've talked about this. In order to receive electric shock, your body's got to act as some sort of a conductor. It gives a path, a complete path, or maybe even a circuit that current can travel through. It's normally accomplished when you touch a bare wire or a live, quote unquote, hot wire, or a live component with one part of your body, and another part of your body comes in contact with electrical ground, or a wire or component with a different voltage potential, and then you become part of the circuit. If your body becomes the path in which the current can travel, doesn't mean it's the least resistance. What it does mean is it as a path. So it's important to make sure that you're taking all the safety measures and putting those in place as you're working on this stuff. Don't become part of that circuit, and it's all too common for guys to overlook that portion. Actual current's going to determine how much injury is actually sustained. The amount of resistance the body has can vary all the time. depending on the varying conditions. The amount of moisture, perspiration on your skin, moisture in the air, if you're standing on concrete or a metal floor, leaning up against a railing, all of those types of things come into factor when you're talking about how much current's actually going to travel through your body. And they'll change the resistance that it has to go through. The actual path of the current through the body and the length of time is going to determine how much injury is actually sustained. For example, if current flows from your finger to your elbow on the same arm, you might experience a lot of pain. However, the amount of current passing through your heart and your lungs can cause fibrillation. What's fibrillation? Your heart basically works a bazillion miles an hour, roughly 300 beats per minute. Not enough to get a full beat. It's really just kind of a quiver. And it stops moving blood throughout your body. It happens at a very, very, very low amperage. We'll talk about that here in just a second. So it doesn't take a whole lot. You go from your finger to your elbow on the same arm. Yeah, it's going to hurt. You go from your leg to your knee or your leg to your hip. Yeah, it's going to hurt. But it's not going through your heart and your lungs. So you might not sustain the same type of fatal injury. It may be long-term or permanent injury, but it may not be fatal. So it all depends on the scenario. If things line up just right, you're going to be in trouble. Let's look at the effect on the body here. If you look, starting up at the top here, we got 1 milliamp. Now, what's a milliamp? Let's keep this in perspective. A milliamp is 1/1000th of an amp. Okay, it's not a millionth of an amp. That's a micro. We're talking about milliamps here. 1 milliamp can cause a slight tingle. Usually nothing's going to be visible on the skin, and normally you're not going to have any bodily damage or permanent damage. But you're talking 1 million, 1/1000th of an amp, you're going to feel a tingle. You're going to know that it's there. That is just bizarre, don't you think? 2 to 9 milliamps, you can get a shock. Normally it's not painful, but think about it. Some of these low voltage shocks that we get, they're not painful, but for the second, we don't realize it's low voltage and we are frightened immediately. We jump, we shake our hands, we don't think about what we're doing. We don't have the time to do that. And secondary related injuries really at this 2 to 24 milliamps become a huge deal. And when I say become a huge deal, they obviously are going to happen beyond that. But the difference between actually doing bodily injury on a shock versus doing bodily injury because you jerked your hand and hit it on all the metal objects inside of that cabinet are going to be way skewed towards a secondary injury, not towards the shock. Once you get beyond that 24 milliamps, then we start to see shocks that actually create damage possibly to the human body or even death because of the shock itself, not because of the secondary related injury. So it's kind of that happy spot right there between that 24 and 25th milliamp. So moving on down, 10 to 24 milliamps, very painful, could have some burns, could lose muscular control. 25 to 74 milliamps, in this area, we could actually get severe contractions. You could stop breathing. You could die for sure. And obviously, you could have visible burns, both where it goes into your body and comes out of your body. At 75 to 300 milliamps, depending on the person, this is definitely a high danger zone. This is where you're most likely to have ventricular fibrillation, so your heart stops pumping blood. The really scary thing there is, painful, absolutely, but you're still enduring it for a little while. So it's a very tough thing to talk about. But if you don't talk about it, if you don't understand that this could happen even at small amounts of amperage, look at it, 75 100ths or 75 1,000ths of an amp can make this happen. And that's real. So when you're out there in the job site and people say this or that couldn't kill you. Boy, I tell you what, hopefully you know better. And go all the way down here to the bottom here. Uh, Over 1 amp, life-threatening burns, paralysis of your heart, death is highly likely. 1 amp. At 15 amps, which is the lowest fuse or circuit breaker size, 15 amps. Uh, the effects of a 15 amp exposure to that electrical current is going to depend on how long that has happened. You know, like everything else we've talked about beyond that 75 to 300, death is almost imminent. You may make it, but most likely you will not. So this stuff is real. Is very, very important to understand the likelihood of imminent death in these scenarios. So again, when talking about electric shock, the most severe, the most potentially fatal circuit for electric current is one that passes right through the heart. So when you think about it, you know, fingertip to fingertip on your left hand to right hand, goes straight through the heart. One hand to one foot, no matter the side, could go straight through your heart. So those types of injuries most likely will be lifelong injuries, but they definitely, most certainly could lead to death. The most common non-fatal injuries that are produced by electric shocks are usually going to be burns. Burns, temporary, permanent vision loss. You could have marks on your body. You know, maybe almost like a welt could be on your body. Most of these are going to require immediate medical attention. Anytime that current passes through your clothing, you may have ignition on your clothing. We have seen some very stomach wrenching videos on YouTube. If you go to YouTube and you just do a search for arc flash, ARC flash, 2 words, you're going to see all your fill of things that could go wrong on the job site. In fact, there's many of them that are on there that are normal mechanical guys or maintenance men on a facility that weren't properly protected with their personal protective equipment or their arc flash hazard suits, and they paid the price. There are some pretty gruesome videos on there. I chose not to show them during this class because I don't want the class to be surrounding that. I want to talk about it. I want you to learn about it, but I don't want to, you know, scare the dickens out of you. And plus, if you're sitting there in your home and you're going through this presentation, your wife or kids may be around you, and I don't want that to be something that they see that's pertaining to something that could happen to daddy when he goes to work, or mommy when she goes to work. So that's why I've chosen not to put those in this presentation, just in case you're wondering. Other forms of burns caused when high amperage current travels through the air, like an arc. Arcs can exceed 35,000 degrees Fahrenheit. That is astronomical. These temperatures, the intense heat and light can cause damage to the skin and, of course, eyesight, as well as virtually vaporizing any of the flame retardant clothing and the metal that's involved. When you look at some of the arc flash videos, you can see that copper and steel and aluminum just vaporize and become molten and fragmented. They become like a bomb. Only that bomb is at elevated temperature, so not only is the force of this stuff exploding out going to do damage, but the heat that travels along with it. It's like a warm knife cutting through butter. It's pretty nauseating to think about that. Electrical components might explode, you know, and we've talked about that already. It doesn't take a whole lot. That molten metal goes in all different directions. And one of the other things that we don't really think about, other than the fragments of this metal and the molten metal and the temperatures and all that kind of stuff, the gases that are put off by the electric burns. So when you look at what you're supposed to be doing on a job site, if it's live, that's really where the issue is here. Going out to a job site, working on a piece of equipment or panel when it's live is where this stuff has the potential to go south. So, in order for you to know exactly what the National Electric Code wants you to be wearing, your personal protective equipment is covered in NFPA 70E, which is the electrician's safety manual, and it will tell you the difference between what they consider to be routine maintenance and repair. And they're also going to back that up and say, look, it doesn't matter if you're out there for routine maintenance or checking or doing a repair. If that unit is live, you're going to have some sort of PPE in order to be in front of it. And oftentimes it's going to be an arc flash hazard suit. So if you're a mechanical guy sitting out there with no electrical license and you're thinking to yourself, an arc flash hazard suit, oh my goodness, there's no way we're going to wear that. That's why you're taking this class. Okay, that's why this class is so important, so that you understand there's more than just going out there and opening up a panel like we've done for my entire career and you may have done for your entire career. There's danger involved, and that danger needs to be handled by somebody who understands how to properly mitigate that or to make it as safe as humanly possible. And that arc flash suit is no joke. They're hard to wear, they're expensive to buy, they're expensive to maintain, and in addition to that, they require practice. So when you look at all of the different aspects of electricity and how they could go south in the mechanical job site, and you're trying to put together a safety program for the year, one thing I'd like to let you in on is what some of the other companies are doing currently, and I would recommend that you do this as well. If you're in a position, meaning your company, to have to occasionally or maybe even regularly wear arc flash hazard suits, what I would like you to think about is, while wearing those arc flash hazard suits, have you ever just tried to do routine checks? Because it's not easy. So, as part of those safety classes or safety programs that you're trying to put together for your internal employees, have them do something simple such as put on your arc flash gloves and take measurements on things that are controlled right there in your shop. Have them practice changing their meter settings and all that kind of stuff. Have them look through the arc flash hazard helmet to work with this stuff, because it's not easy, and you certainly don't want the first time that you've ever done it to be on a job site where your life is at danger, because it's very difficult. Some of the precautions, well, when you look at some of the precautions, most tools and pieces of electrical equipment, especially if they've been approved by UL lab, Underwriters Laboratory, they're provided with protective insulation, barriers, and safety devices. They can't protect against unsafe, careless, and take a chance kind of guys that are out there on the job site. And the protection that that tool provides is only up to a certain point. You get into the elevated amounts of amperage that you're working on or elevated voltages, you start to get into that category that needs special tools to work on it. So you want to make sure that your tools are appropriate for the given job site, or that you are able to have access to those types of tools. Common sense is going to dictate that you should never touch bare electrical wires or connections. That should be common sense. But if possible, the other thing you should be thinking about is, don't work on hot equipment if you don't have to. Don't do it just because it's easier than going down and shutting off the switch. I understand that there's instances when you have to work on hot equipment or live electrical equipment. You go in some of these larger industrial plants or manufacturing plants, and they're going to have $1 million processes that if you shut them down, they're losing thousands or tens of thousands of dollars every minute that thing is down. And so they want somebody that's going to work on it hot. I understand that. That's probably going to be electricians, not mechanical guys. But if you go down and shut this thing off, make sure you're following lockout, tagout procedures, which we'll talk about here in just a little bit. Keep yourself dry. Don't be working on this stuff out on a rooftop or the side of a building when it's damp or wet. Don't lean on the walls when it's damp or wet. Notice when your body is starting to perspire. Now that seems pretty ridiculous, right? And it seems obvious. If it was that obvious, I wouldn't bring it up. If it was that obvious, we wouldn't have people that are getting injured or killed every year that are statistics on OSHA.gov. And so that's why it's important to bring us back to the basics and really remember this stuff. When it comes to electrical safety rules, there's only a couple of them. Don't be a conductor. Should be number one. Don't bridge that gap between two electrical connections in which you now become part of that electrical circuit. Stay dry. Avoid working on electrical equipment when you're wet or if your shoes are wet. Don't stand in any kind of puddles or wet ground if possible. Wear rubber-soled shoes. Don't wear any jewelry. Watches, rings, metal jewelry, things like that. They can catch in the machinery, and all by itself, that can be a hazard. But they also could conduct electricity. And if they're conducting electricity, for instance, like a watch, now you not only have a shock and an entrance point, you've got an entire band around your wrist that now could become electrified and amplify all the effects of that electricity. So don't wear any jewelry when you're out there. When you're working on ladders, make sure you use an appropriate ladder. Don't use a ladder that's made of metal pipe or any kind of metal. Use something that's wood or fiberglass that's suitable for potential work around electricity. One hand in the equipment at all time. Okay, the electric path won't go through your heart if you only got one hand in there. And you're wearing rubber sole shoes and you're not standing in water, things like that. It's not a foolproof plan. So I'm not saying it'll never happen. But the whole idea here is not to prevent every single person from committing an error. Things go sideways all the time. You can't control how the equipment's going to react. The purpose of this program is to minimize damage to the human body or, again, the building. So if you're only using one hand in the equipment at a time, you're minimizing your chance for that electrical circuit to be going from one arm to the other arm through your heart and potentially kill you. Be able to identify those electric hazards. Avoid being that path of least resistance so you become any path. Don't expose your body to two different voltage potentials. That can be just as bad as touching a grounded object with your hand on an open wire. If you've got two different voltage potentials, they're going to try to equalize. And if you're the object that they can travel through, you're also going to be the object that they're going to equalize through. When you're talking about circuit protection, fuses and circuit breakers by far are the most common forms of circuit protection we've got. So what's the function of fuses and circuit breakers? Well, obviously to protect the wiring connected to the equipment. That's one purpose for them. Second, protect the equipment loads. And the last thing, protect health and life. We know that. So when you recognize the fact that a 25 milliamp circuit in your hand could be fatal, then you realize that even circuits with half an amp protection could also be lethal. Never mind 15 to 20 amp protected circuits. So where would you find a smaller amperage type circuit? Well, smaller breakers. Smaller, and when I'm talking breakers, I'm actually talking pop outs, The smaller fuses is another one where you could run into circuits that have smaller amounts of amperage, maybe on a circuit board. Those things can also be lethal. Doesn't mean they always are, but the idea, again, minimize the potential that you're exposing yourself to. When it comes to overhead wires, make sure you've got a safe distance. Oftentimes, if we're going into a facility, we have ladders on top of our vans. And when we've got ladders on top of our vans, sometimes our ladder racks stick up farther than the ladders themselves. You got to know where that is. Don't be bridging the gap between the ground and that overhead wire with your vehicle. Anytime that you're out there on a job site that's using cranes that have booms or cables, make sure that you're standing very clear of those facilities. We see that all the time when we've got condensing units being boomed up onto a rooftop. There's always a potential to be involved in a crane accident when it comes to electricity, and you know, if you're interested in some of those videos, there's quite a few of those on YouTube as well. Make sure that anytime that you're dealing with overhead wires, you also understand that standard PPE that you would be wearing, personal protective equipment, may not be sufficient in any way, shape, or form to the type of power you're going to submit yourself to with an overhead wire. One thing that a lot of us have been conscious of through the years, but we've also been guilty of through the years, is being up on a rooftop in which we've got high voltage cables up on the roof, and instead of going around, which is way down by the edge of the roof, we step over them. Be very careful. Exposed wiring. Anytime that you've got exposed wiring, loose connections, loose terminals, poor insulation, that always can create an issue. That's no surprise at all. So anytime that you've got those types of scenarios, correct them. Correct them where appropriate, I should say. In speaking with mechanical guys, your correction is going to be limited. Oftentimes, in order to correct those issues, we've got to have an electrician on site to do that. So make sure that you know your place. Not all of us should be working on everything. If we're not licensed to do it, then we're not going to be licensed, to do it just one time. It's all the time or nothing. And if you don't have a proper electrical license, most oftentimes, especially for us mechanical guys, you're limited to everything, whether it's replacing a wire. Some places you can't pull two wire or even thermostat wire without a full-on electrical license. Some places you can replace a circuit breaker, but that's all you can do in a panel. You can't ground anything. You can't terminate your bond, any of that kind of stuff. So know what the requirements are in your area. Don't overload circuits. Boy, isn't this a hazard. We see this all the time, even at our houses, guys. Uh, Too many devices on a single circuit. It generates a ton of heat, and heat obviously relates to fire. The sheathing will get dry, cracked, or maybe even melted. Then we expose the wire, and once we expose that wire, it's not too long before we create even more of a hazardous potential in which somebody could get electrocuted or a building could start fire. Make sure that the circuit is properly sized to prevent any kind of damage. And then also, from a mechanical standpoint, these circuits are not as easy for us to deal with as what they used to be. You can't just take out a two-prong circuit and put in a three-prong circuit like we used to. Now we got to take into consideration they have to be grounded. We've got to have GFCI protection. We have to have arc fault protection. And granted, from one municipality to the other, they may change what those requirements are a little bit. But if you look at the broad scope of things, those are reasons that us mechanical guys are not allowed to work on a lot of the electrical stuff, because there are a lot of intricacies in the electrical code that we just don't work on enough to understand what the code says, and so we're not licensed, and we really shouldn't be working on that. Anytime we've got a circuit that's overloaded, meltdown is imminent. We see that quite a bit in the cube farms. office buildings where they've got lots of call centers and cubicles, is what I call in cube farms. You'll see in the wintertime, they obviously can't heat or cool that place to accommodate 1,000 people. So oftentimes in the wintertime, that's usually when you see people trying to do things to keep themselves warmer than the guy next to them or whatever. So you'll see underneath the cubicle, they'll have a little space heater. Oftentimes that space heater is going to have a long 5 foot cord or whatever, 6 foot cord, and they don't have that much room under there. Don't want wires everywhere, so they're going to wrap that thing up, maybe put a twist tie or a Velcro strap around it or something like that. Well, we're creating a right potential where we could have a meltdown. We could create an overamping situation there in which the sheathing could melt. We could have an arc or a spark, and boom, now we've got a fire. Some of the examples we run into, in addition to having the under desk heaters, if you will, would be holiday lights. We see holiday lights out, uh, and we'll have one circuit running several strings of lights. And even though you might see one or two things plugged into that circuit, how many extra light strands are plugged in consecutively, one after another, after another, after another. It creates a tremendous load on that circuit, and could definitely create a situation in which we've got a right potential for fire. Make sure that you're up to scuff with local codes for your limits that you're allowed on your house for Christmas lights, or inside of a commercial building. Some places restrict being able to put on those GFCI protected outlets. Some of them will only restrict it if the GFCI protection is not there. So know what your local code allows for those particular devices. Electrical work, fitting, right? Could be shocking. Make sure you use the proper equipment for the proper load you're working on. You shouldn't be using handheld instruments for anything greater than 600 volts. And guess what? For us mechanical guys, no electrical license, we shouldn't be working on 600 volts anyway. It's awfully hard to turn down work, especially when things are slow. So if you get out there on these industrial buildings where you're running high amounts of voltage, which in turn run higher amounts of amperage, please, I implore you, know your place. Uh, Kindly defer the electrical portion of that over to an electrician, and come back and diagnose the mechanical side of things or the ventilation side of things. Make sure that your capacitors are properly discharged. The days of throwing a screwdriver across the prongs on a capacitor should be long since gone. We've heard the horror stories of them popping or blowing up. They do have bleed off devices for those, so make sure that you're utilizing those so that an accident doesn't occur. They can hold a charge for quite some time after being connected. Power off any adjacent circuits. Why would that even matter if you're powering off circuits that are nearby? Well, there's something called induction. So if you've got power wires that are running next to each other, but even though they're not connected, you've got a magnetic field that runs around them. We know that there's a magnetic field there because we use those little pen lights to detect whether there's voltage present. The pen light, when you think about it, you take the little meter, the little pocket meter out of your pocket, and you put it next to a wire, and it lights up at the end, maybe even makes a beep beep noise. What's actually happening is inside of that little pen light, you've got a circuit powered by a battery. But at the very end, you have contacts. Once you get that pen light inside the magnetic field for the wire, it closes that contact. And when it closes the contact, the battery energizes the light and the beeper, and you know there's power there. And some of them are smart enough to know different ranges of power, so they give you different beeps and different sounds and lights based on what power you're talking about. So make sure that the adjacent circuits are shut off, because that magnetic field can also do what's called inducing power, inducing voltage onto the other wires even though they're not powered up at all. So we've seen that for years with cable wires. People run regular power wires with their cable wires across a ceiling or through an attic. They strap them together to make it look nice. Well, in reality, even though the cable wire doesn't have power on it, it gets power onto it and it ends up messing up the TV or the cable box because of that induced voltage that is on that power line. So make sure you're taking care of yourself by shutting off any adjacent circuits. Properly disable power before you're working on this stuff. And by properly disabling it, do it yourself. Never send a customer down to shut off a breaker or a blade or knife switch or anything like that. Always do it yourself and use your lockout, tagout lock that's properly tagged and filled out so that you can be the only one that's going to remove that and you know exactly what's turned off. When it comes to grounding, you want to make sure that grounding protection's installed. All electric systems and equipment got to have some kind of grounding protection to help prevent the unintentional energizing of any metal components within the system, including the boxes, the switches, the motors, the conduit, possibly even metal pipe that's adjacent to it, like copper. The grounding system should be at 0, allowing the current a safe path of least resistance in any case is what you want to do to ensure that if the system becomes energized, it's going to trip that breaker. Now, there's a difference between a grounding path and an effective grounding path, and if you don't know the difference between those two, that's why you should defer to an electrician in dealing with some of this stuff. The effective ground path is one you put in there on purpose that is there as a preventative measure in case the metal parts do become energized. We want to make sure they're connected all the way back to the breaker panel so that way the breaker trips. If we have a break anywhere in there, there's a possibility, and I know as mechanical guys you've felt this before, that the conduit or the box could become energized and never trip a circuit. It just sits there and it's powered up and it generates heat, which could lead to a fire, but oftentimes it leads to shock, and it's to one of us. We've felt that before. All metal objects have that shock potential. Proper grounding is going to prevent that shock potential. And when it comes to bonding principles, I'm going to defer that to NFPA 54 sections 7.13.2 when dealing with CSST. It's very important that you remember that. NFPA 54 section 7.13.2, in which it says CSST, corrugated stainless steel tubing, gas tight, track pipe, diamond pipe, things like that. Any length of CSST has to be bonded, beginning with the first downstream fitting from the source to the first fitting on the length of CSST. It doesn't get any easier than that in my own mind, but there are lots of different interpretations of what they're actually talking about there. Be aware of what your code official actually wants as far as the bonding goes. That's hugely important. Bonding simply connects metal objects that could potentially carry current, and it gets rid, when you connect them, it gets rid of the potential difference between there, and if there's no potential difference, there's no reason for it to arc or spark. So that's why you're bonding. It's important to realize that it is code and it is enforced in most areas. However, code officials will enforce this in a little bit different way in different areas. So make sure you understand what they want. And in most areas, guess what? Mechanical guys can't do it. Not physically can't do it, but by licensing reasons, they can't do it because they can't terminate that bonding wire properly because it's going to be inside of that panel. Check the ground prong. Understanding that the grounding prong's got to be present. You're talking a 3-prong cord here when it comes to the grounding prong. Don't cut that thing off. With no grounding prong, there's nothing to trip that breaker. There's nothing as a life safety measure for you or the homeowner or the building worker. So cutting that cord, again, against code and really against moral beliefs. Yeah, it makes it easier to plug into 2-prong receptacles, but they do make adapters for that. Don't cut that prong off, especially anytime that you're out on a job site that's not your house. We can't control what you do in your house, but I would say, even in your own house, do not cut that plug off to make it easier for yourself. That's a safety measure. When it comes to wet conditions, work as little as possible in wet conditions. Anytime you're in wet conditions, the risk of shot goes up extremely high. And anytime you're installing things in wet locations, one of the things you got to think about is it in a location that requires waterproof wires and connectors, and also wet-proof tools. So those things are always something that you got to take into consideration. Anytime we're talking about wet conditions, ground fault circuit interrupters come into play. Ground fault circuit interrupters have been code requirement for a very long time now, and they have taken over areas inside of a home. You're now going to see the GFCIs installed in bathrooms and unfinished areas of the basement, garages, outside your front door, outside your back door. So they're all over the place. And the one thing to keep in mind with GFCIs, the way they work is very interesting. There's a reason they want them in wet locations. It doesn't just trip on a short. Okay, that's not what we're looking at here. It trips based on the amount of amperage going out and the amount of amperage coming back. You could picture it as a hot and a neutral wire. If the amount of amperage going out and coming back is different, and the difference equals 3 to 5 milliamps at least, then the GFCI is going to trip. Now, if I become that circuit and I hold on to the hot leg and the neutral leg, and the circuit just goes straight through me and on back to the source, I may not change the incoming and exiting amp draw, so it won't trip. And that's why it can't be the primary life-saving device. It is a life-saving device when you're talking about where it's located and how it's supposed to act and things like that, secondarily. But when you look at these things, they're very interesting, and that's why you're going to see them all over in a house. And that's a requirement by code. It's easily said now that any place that's not GFCI protected in a home is going to be arc fault protected. Well, we talked about lockout, tagout programs a couple of times, and it's important to bring it back up just to close out the rest of this class. Lockout, tagout programs are mandatory for everybody. You have to have a way to shut off the breaker, the panel, what have you, with a proper lockout, tagout device that has tags on there that tells who the actual person is that's locking it out, the date that it was locked out, things of that nature. You gotta do this because you want to make sure somebody else isn't going to come along and say, "Oh, it's hot in that office. This must be why it's hot. This breaker's off," and turn it back on. Well, if there's a lockout tagout on there, that is pretty universally accepted that it's something that somebody should leave alone and not mess with, or even try to mess with. When it comes to lockout tagout programs, they those programs require periodic safety training. They've got detailed procedures they want you to follow that aren't going to be addressed here in this program, but they are worth looking into so that everybody in your company is on the same page. You know, some of those things that you could be looking at is what type of lockout tagout device would I need to have, you know, based on the type of work that I perform. What type of information needs to be on the tag? Will we have the ability to pass these tags off from one person to the next? Well, each individual is supposed to have only keys for their lockout tagouts, but you have to have provisions if the end of the shift comes and the work's not done and somebody else is going to take over. There has to be a provision to allow you to pass the torch, if you will, from yourself on to the next person that will need to fire that unit back up once the work has been performed and done.